Okay, so let's talk about the density of states. The electron is if the electron is in the energy band, then we can talk about how many electrons is in per per 1 centimeter to the power of 3 per energy, and we can derive the density of states in one-dimensional and two-dimensional and three-dimensional, but we are living in the three-dimensional, so let's talk about three. When we calculate this, it's proportional to the root x, which means the x is the distance from the atoms, and if the semiconductor is p-type, then the density of state is proportional to minus root distance. And if the dimensional is keep decreasing, then the starting of the energy is big. The next concept is the Fermi-Dirac distribution, which means the probability of the electrons in the energy band. And when we want to know about how the number of the electrons in the energy band, we should know about the probability and the density of states. And when we multiply those two, we can know about the number of the electrons in some specific energy state. The formula is in the textbook, and if the exponential factor is really big, if the exponential factor is larger than is way more larger than 1, then we can neglect the 1 in the denominator, and that factor names the Boltzmann belt. And when we multiply the density of states and probability, we can plot in the EK diagram. And we should be careful about this because the valence band and conduction band, the x-axis of the valence band and conduction band is distance, but the x-axis for the density of states is not a distance, it's a density of states. The y-axis is energy, so we should be careful about confusing these two. And there is only two types of semiconductor, n-type and p-type. So when we want to know about the p-type electrons, p-type semiconductor function, the probability, then we should calculate 1 minus n-type probability. And the intrinsic Fermi energy is the criteria of the energy. So when the semiconductor is doping with the n-type, then the Fermi energy is close to the conduction band. And when the semiconductor is doping with the p-type, then the Fermi energy is close to the valence band.